So with any measurement that you make in this class or in life, there's always going to be some level of uncertainty about that measurement. No matter how precise the instrument is, the instrument's going to have a limit on how precisely it can take a measurement. And so at some point, you're going to be estimating and you're going to have some sort of uncertainty in that measurement. And that's the idea behind recording measurement uncertainties and then propagating them with calculations. So for this video, we're just going to look at the rules we're going to use in IB chemistry to determine uncertainties on measurements. These may not be perfect, they may not be the most advanced, but these are the acceptable rules for the DP chemistry class. So first, with digital instruments, things like digital balances or temperature probes, any of the Pasco probes that we use where a measurement is actually displayed on a screen. The way we're going to do it is we're going to take the smallest increment and we're going to do plus or minus 1 of that smallest increment on the digital instrument. The idea being that the machine itself is actually rounding off to give you whatever that last measurement is, that last part of the measurement is. It has to round up or down itself, and so that's why that part of the measurement is going to be uncertain. So in this digital balance, it may be hard to see, but there's 1 decimal point and then the 0 comes after that. That's the 10th place. And so the uncertainty comes in that decimal place, the 10th place. And so we're just going to say whatever mass we get on this balance, we're going to include along with that, writing down that mass, plus or minus 0.1 grams. In this one, because it goes to 2 decimal places, we would say plus or minus 0.01 grams. So this digital balance gives us more precise information and therefore also has less uncertainty. This one is uncertain in the 100th place, where this one is uncertain in the 10th of a gram. If we have something like an analytical instrument, mainly for us this will be glassware, then the system that we'll use is that the uncertainty of the measurement is half of the smallest increment of that instrument. So on this one, if you see the main line here is 6 and the main line here is 7, and I'm just going to go ahead and guess. I could count that there's 10 increments in between the 6 and the 7. So that means the smallest increment is 0.1 cm cubed, which means my uncertainty, I'm going to report that as half of it. So I'm going to report the uncertainty on this graduated cylinder as plus or minus 0.05 centimeters cubed. A centimeter cubed, remember, is the same thing as a milliliter. So you just have to look at the instrument and then look at the smallest increment. So between these lines here is the smallest increment, or between this line and that line. And each one of those increments represents 0.1 cm cubed. So we're going to cut that in half to get our uncertainty. Sometimes there's only going to be 1 increment on an instrument, and so in that case, usually the manufacturer will actually report the uncertainty to you. So this is a pipette, and I just drew over it, but on an instrument like this, you can see that in small print it says plus or minus 0.06 mLs. So a pipette is one of the more precise instruments we have to measure volume, especially smaller volumes, but they can be quite large. But this one can measure 25 mLs of a liquid, and it's only plus or minus 0.06 ml. So it tends to be more precise than your average graduated cylinder that is this size. This thing on the right is called a volumetric flask. It's really useful for measuring large volumes very precisely, and you should be able to spot the uncertainty on here as well. It's right up there. So for every liter, there's only plus or minus 0.80 mLs of uncertainty on this device. That pretty much covers the ones we'll commonly see, but every now and then we're going to get an instrument. This comes up with a lot with digital instruments, or it comes up when we're trying to time something and we have to factor some sort of reaction time into our measurement. In these cases, sometimes we'll get a digital instrument where there will be fluctuation, meaning that the reading isn't staying still. Maybe we're using a balance that reads to 5 decimal places, and so the slightest little jostling of the table or a little bit of wind in the room is actually enough to make the measurement go up and down. And so the best we can do in cases like this is that we're going to watch the instrument for a while, and we're going to try to actually pick out what is the max value and the min value that we've seen as we're trying to take the measurement. So we're going to take the max and the min values. We're going to subtract those two values, and that's going to give us what we call the range of values. And so that will tell us, okay, well, this instrument is measuring really from this value to that value. That's the range. So our uncertainty is half the range. Because then when we report that as a plus or a minus, it should include all of the values that we've been seeing on the scale. So we can't just take a stab at the middle and say we know it exactly to this value, because really, if it's fluctuating a lot, that implies greater uncertainty than maybe we would have immediately expected. So this could happen, again, as an example, on a balance that reads to a lot of decimal places. And so even though our first rule here is plus or minus 1 of the smallest increment, if an instrument like that is fluctuating, then actually we're going to use this method, that half the range equals the uncertainty, because there's actually more uncertainty than that first rule suggests. The last thing that we have to do is we need to round off properly when we are dealing with uncertainties. So in this class, any uncertainty that you give should only ever have one significant digit. So actually, this example up here, we wouldn't report that this way. Instead of giving that 0 afterwards, we wouldn't include that 0, and we would just write plus or minus 0.8. Another example is that we're not going to have an uncertainty that is plus or minus 1.5. So there's 2 digits here that are uncertain. And the idea being, if this is uncertain, if I'm uncertain in the ones place, then I'm really, really uncertain about the 10th place. And so I really shouldn't be reporting anything about the 10th place, because I don't even know about the ones place. So if we cut an increment in half and we get more than one decimal, like 1.5, then the idea is that you would round. And so you would probably round this to plus or minus 2, the closest increment. But now we're just showing that we're uncertain in the ones place instead of uncertain in the 10th place. So as a general rule, round off your uncertainties so that you're just uncertain in one spot. And then finally, make sure that the precision of your actual measurement itself and your uncertainty match. And what I mean by that is, if the balance reads 2.02 grams, but because of fluctuations, you decide that the uncertainty is actually plus or minus 0.2 grams, well, you're uncertain in the 10th place, in the first decimal place. That means you're uncertain here, which means you have no business telling me anything past that 10th place. And so actually, you need to round away any extra digits that you get so that you have the same number of decimal places in your measurement itself, the 2 gram measurement, as you do in the uncertainty that goes along with it. So this will happen occasionally with glassware. It can happen with those fluctuating instruments. And it's going to happen when we do calculations and we use the calculator. So those are the rules. There's some practice at the bottom that we can try in class. Digital instruments, analytical instruments, stated on instruments, and fluctuating/average values. And make sure that you round off to 1 digit of uncertainty and that your measurements match the uncertainty of the uncertainty itself.